Now we're going to talk about floating point variable types in C, specifically C89. Now this is going to be a simplified version of how floating point works. There are entire books devoted to floating point representations and some of the trade-offs that are made and how decisions are made in the standard that's used, which is Ieee 754 and such. So you don't really need to know all that, I don't think, to do most of what you need. And plus, that would just be too much to try to cover in a single video anyway. So in ANSI C or C89, we have two floating point types. The float, so that's a keyword, and double. And we've already been using double. Now float uses 4 bytes of memory, and a double uses 8 bytes. So when you choose one of these over the other, part of the decision is how much memory to allocate, and the consequence of that ultimately is what numbers can be represented. So each of these are used primarily for representing numbers that have decimal portions, but as we'll also see, they can represent numbers much larger than an int because of the way things are stored. So I think the first question ultimately is, what do we mean by floating point? Well, floating point is versus fixed point. So let's say that, and to keep this simple, in our computer, we have 4 positions to store digits. And since we're wanting to potentially store numbers with decimal parts, we put the decimal point right here. So I could store the numbers 00.00, 00.01, 00.02, all the way down to 99.99. And for this discussion, we ignore signs. So we won't have any negative numbers. It's just numbers in this range. All right? So how many numbers are here? Well, I have 10 values that could go in this position. And to the left of that, there's 10 values there. So for each of these 10, there's 10 here, so we're up to 100. For each of those, there's 10 of those, so we're up to 1,000 and so forth. So this ultimately comes out to 10 to the 4th, which is 10,000 different numbers being represented. But one of the things you'll notice is I can't represent numbers outside of a very small range. This only goes from 0 up to 99.99. So what if I want to store something larger, something like, 2,300? Now you could argue that, well, this is only 4 digits, and these are 4 digits, but these 4 digits are all to the left of the decimal point. And so this decimal point here is fixed. That's why we call it this. So even though I'm using the same amount of memory in both cases, for 4 positions of numbers, I can't shift the decimal point from being here to represent this particular number. So floating point is intended to address that. So how does that work in a simplified form? Well, floating point is similar to scientific notation. So if I have the number 123.45, if I want to rewrite it in scientific notation, I move the decimal point to the left here over 2 places. So that way there's one number to the left of the decimal point, and it becomes 1.2345 times 10 squared. And we could go the other way as well. So what's important here? Well, if I know you're always going to have this form where you have a leading digit, followed by the decimal point, followed by any other numbers, and then the exponent, really what I need to store is the 1, 2, 3, 4, 5, which we call the Mantissa. and the exponent, which is a 2 in this case. So let's go back to my other example where we want to store 2300. So in scientific notation, this would be 2.3 times 10 to the what? 1, 2, 3, 10 cubed. So if, once again ignoring signs, if I want to have still 4 positions of values, but this one right here is the exponent, what I could write is 2303, because you know ultimately this is 2.30 times 10 to the third, which is 2300. So I have a much larger range of numbers, and in fact, using this scenario, I could go all the way up to 9.99 times 10 to the 9th by writing 9999 here, with this being the exponent again. So can I represent more numbers than before? Well, no, I still only have the 4 positions, so I still only have 10,000 unique combinations of those 4 digits, but the range of values is much greater because this is a pretty big number as opposed to 99.99. So there's a trade-off. There's actually going to be some holes in here, so there will be some numbers I can't represent at the expense of representing a larger range of values. And that's what we're getting by using floating point representations. All right? So that's sort of the basics of how floating point works. Now there's one big difference between what I just showed you and how it really works, and that is in my computer we use a binary representation. If you watched my video called Bits, Bytes, and Number Bases, we talked about the fact that for the way we typically write numbers, we have a decimal point or a radix point, if you want to be more general. And if my number base is B, then to the left of this, I have the B to the 0 column. To the left of that, to the B to the first column. To the left of that, to the B squared column, and so forth. But to the right of this, I have the B to the -1 column, the B to the -2 column, and so forth. So that means if my base is 10, which is what we normally use, which is decimal, right? This is decimal. When I write the number 0.3, we say this is 3/10, because it's 3 times 1/10, because 1/10 is equal to 10 to the -1 power. It's B to the -1, where B is 10, so we get that right there. So other bases can do the same thing. So if I have this number right here, 0.1101 in base 2, what does this mean? Well, the first one here is 1 times 2 to the -1 power. It's in this position right here. And the one to the right of that represents 1 times 2 to the -2 power. The 0 to the left of that is 0 times 2 to the -3 power. I'm including that as a placeholder so I don't get confused. And finally, the rightmost one here represents 1 times 2 to the -4th power. So what these are is 1 times 1/2, which is equal to 0.5. 1 times 1/4, which is equal to 0.25. 1 times 1/8, which is equal to half this, which is 0.125. This one, though, I won't need, or excuse me, 0 times that. So that won't be included in my sum. And then finally, we have 1 times 1/16, which is half of this, so it's 0.0625. So what do these add up to? Well, the first two add up to 0.75, And so now if I add my 0.75 with this, I get 5, 2, 1, carry the 1, 8. 0.8125 in base 10 is what this representation is in base 2. So inside my computer, when I'm representing a number as a float or a double, it's really as some combination of powers of 2. All right? So let's talk briefly about the Ieee Standard. Although for this video at least, I'm not going to go into a lot of detail because it would be a lot of detail. So in 1985, the Ieee 754 standard was released. And this is the floating point standard that modern computers use, with some updates since 1985, since that's been 35 years. Before that, different computer manufacturers may choose to make different decisions on how floating point works. One of which is, how do you round off? You think you know how to round, but it turns out there's lots of different ways to round. If you check out the Wikipedia page on rounding, I think they have 10 different ways. Sometimes you round up, sometimes you round down, sometimes you round towards 0, no matter which side of 0 you're on, all kinds of things. And they each have their place. But with a standard, if anybody follows it, then we should get the same answer for the same calculations. Prior to that, different computers might produce slightly different answers. So the Ieee 754 standard defines a number of data types. And so one of those is called single precision. And another of those is called double precision. There's actually more than that, but in C, we'll create a table here. In C, single precision is represented by the float keyword, number of bits we'll put here, and that's 32 bits or 4 bytes. And in C, double precision is represented by the double keyword, which is 64 bits or 8 bytes. So how does that work? Well, the numbers are made up of 3 components. So on the left most bit, we have the sign bit. So like minus 12.34, we need to represent the sign. To the left of that, we have the exponent. So if I do the conversion where I represent powers for shifting the decimal point, this is stored here. And then finally, the last part, some people call it the Mantissa, or other people call it the fraction, based upon some decisions that are made about what you actually store from this. But nonetheless, it's broken up into 3 parts. So of course, both of these have a sign bit. So for the sign, we have 1 bit for each. For the exponent, single precision devotes 8 bits to that, and double precision devotes 11 bits. And finally, for the fraction, we have what's left over from the 32 bits. So for single precision, it's 23 bits, and double precision is 52 bits. So these trade-offs in how many bits are devoted to the exponent and how many bits are devoted to the fractional portion of what you have determine the range of numbers you can represent, as well as the particular numbers you can represent. So for single precision, right here, in base 10, you can represent approximately plus or minus 10 to the plus or minus 38th power, which is a huge number. For double precision, you can represent plus or minus 10 to the plus or minus 308th power. And I can't even imagine really what that represents. But that's most of what I'm going to say about the Ieee standard, because there are books devoted to this. So let's talk about some other things and look at some code. In fact, let's go to the code part now. All right. So let's do something. Let's say double D equals 1/10. Now, if I just write it like this, we're going to have a problem. And what's the problem that we have here? This is integer division. So 1 as an integer divided by 10 as an integer gives me an integer. In this case, it would be 0. So what I'm really going to do is write 1 divided by 10.0. 10.0, by adding the 0.0, tells the computer to make this a floating point number. And so when I have an integer divided by a floating point number, I get a floating point number. So let's print off the value on that. Or sorry, this F. And let's make it 2 decimal places. So I print. So that's 1/10 like you'd expect, right? Let's change this now to 15 decimal places. Looks fine. Change it to 20. Uh-oh, what happened here? Well, it turns out that if I use a finite number of powers of 2, I cannot represent 1/10 exactly. The same thing happens in base 10. If we look at something like this, base 10, the number 1/3 is exact. But what if I want to represent it as a decimal number? Then it's 0.3333 forever, right? It takes an infinite number of 3's here to represent 1/3 exactly. Because what this really is 3 times 1/10 plus 3 times 1/100th plus 3 times 1/1000th and so forth. But I can't write this forever. So I have to have a finite number of decimal values to store in a computer. I can't store an infinite number of positions. So in base 10, I cannot represent 1/3 exactly as a decimal number. Well, it turns out in base 2, I cannot represent 1/10 exactly. Because how do I do it? Well, it has to be some combination of powers of 2. So we know 1/2 is equal to 0.5. So that will be out to represent this, because this is 0.1 in base 10. 1/4 is 0.25. That's too big. 1/8 is 0.125. That's too big. 1/16 is equal to 0.0625. That's less than this. So if I'm trying to represent 1/10 in base 2, I need placeholders. So I have 0.0001 just to get up to this. And then I would need to add additional powers of 2 to try to represent 1/10. Well, it turns out I would need an infinite number of these in this case, just like I need an infinite number of these in this case. So that means that for numbers you're used to representing in base 10 without problems, like 1/10, you can't necessarily do it in base 2. Let's come over and look at another problem. So you say, okay, you showed me that problem. Let's try this. Let's try the 1/3. So just like before, I'm going to say 1 divided by 3.0. And let's create a float. We'll call it F. That's also 1/3. And let's write some logic to compare. If D is equal to F, they are equal, else print D, say to 15 positions, 0.15F. So we use the same format specifier for each of these if I'm printing. If I was using scanf, I would actually have to use something different for one of those for the double. So let's see what happens. Oops, and I left out new lines. Uh-oh, they're not equal. And so if I print out enough decimal places, you can see they're not the same. Even in the double, I'm not really, I assume, be able to represent 1/3 exactly. I'm just not showing enough decimal places to be able to see it. And at some point, we won't really be able to show all the decimal places anyway, because it's not an infinite number of things. So this even stopped looking like 1/3 after we got to a certain point. But it stopped looking like 1/3 at a different point than the float representation. So if I'm using these numbers, if I only care about up to a few decimal places, then they're both probably fine. But internally, they're different. So why is that? What's the problem here? Well, there's a couple things going on. One is the float has less bits to try to represent 1/3 as a combination of powers of 2 than a double. So they both probably need an infinite number of bits, and because we use fewer, we can't represent the same numbers. But there's something else going on here. Right here, you may look and say, I'm comparing a double to a float, but I'm actually not. In order to compare these, they have to actually both be the same type. And so what the computer will do is it will promote the float to type double. So this F is converted to a double. So you say, well then, if they're both doubles, what's the problem? Well, let's see what the problem would be. So let's think about this. And let's keep things in base 10 to understand. So imagine I have a variable type, D, that can represent 4 decimal places. That is 4 places to the right of the decimal point. And I have a variable type F, or a variable of that type, that can represent 2 decimal places. So when I write D equals 1/3, what I really get is 0.3333 in this case. But when I write F equals 1/3, I get 0.33. So those aren't the same. But in my code, when I wrote this, I said that the float gets promoted to type double. So it wants to turn this into something that has the 4 decimal places in this simplified example. The problem is, what does it put in these 2 positions? Because there really were a lot of numbers that when rounded off to 2 decimal places could have been this. I could have had 0.330, 0.331, 0.332, and I'm only showing a 1/3 decimal place. What if I had a bunch of others? But we also could have had this if we round off in the conventional way, 0.329. All of these, if we round off in the normal way, that looking at this digit, if it's greater than 5, we round up, and if it's less than 5, we round up, down, or 5 or greater rounds up. All of these then would be rounded off to this. So even if we say we're going to add 2 extra decimal places of value, what does it put in these 2 positions? Well, I don't actually know, but let's say it turns the second one into this, 0.3300, to show those spots. Well, that's still different than 0.3333, so they're not the same. So the consequence of that is that in programs where you try to compare floating point numbers to something else, and it's not just a float to a double. If I come in there and do something like this, sorry, I can't see. If I try to change this to is D equal to like 3.0, I'm still comparing this to something, and I may have trouble getting that exactly. Let's see an example of that actually, because of how things work. I think I may have done this in an earlier video, but I can't remember. But we'll do it again. Let's do a primitive form of root finding. Root finding. So if I have this expression, x squared minus 11x plus 24, we could factor this into x minus 3 times x minus 8. So I got x squared, x minus 8, or excuse me, minus 8x plus minus 3x is minus 11x, and then finally negative 3 times negative 8 is positive 24. So if I want to find the roots of this, I should get 3 and 8, which are both integers, right? And I can represent those. So what's the problem? Well, I'm going to use a primitive form of root finding. So what I'm going to do is I'm coming here and say double x equals 0. If you want to say 0.0, it won't really matter. We'll start there, and what I'm going to do is I'm going to try values of x in the range of 0 to 10 and see which of those, when plugged into this equation, give me y equals 0. So we're trying to solve this. All right? So we may do this. We start x here. So I'm going to say while x is less than or equal to 10.0, we're going to increment in steps of 0.1. So I'm going to start off by testing x equals 0, then I'll try x equals 0.1, then x equals 0.2, and so forth, all the way up to 10. And on each iteration, I'm going to ask this question: if, let's write the equation first, y is equal to x times x minus 11 times x plus 24, if y is equal to 0, let's print y. So we should get 3 and 8 as the roots. We'll try that right there. Oops. Didn't define y. So now I have my y. So what happened? Nothing printed. Nothing printed because y was never equal to 0. So let's take out this now. And let's just print every value of y and see what we get. And let's do a little formatting. This looks like it's 0. Let's do this. We'll make this so say y is equal to this, and x is equal to 0.2f. So where does it change? Oops, sorry. Here's one of the places it changes, right? So look here, minus 0 point, a bunch of zeros, and then there's a 7. So it's not equal to 0 at the value of x equals 3. And then what about 8? Same type of thing. Here's a 57 at the end. So if I show more decimal places, if we don't worry about lining up, right here. So it's never exactly equal to 0. Therefore, there's a problem trying to do a direct comparison. So what's the solution in this case? Well, what we're looking at in the case of roots is I have a function that does this. So we're looking at this point and this point. So this is 3, this is 8, right? If we zoom in, what happens, I'm testing points. So if we zoom in like this, and here's the line, I might get a value of y that's here, and then a value of y that's here, and then a value of y that's here, and so forth. But I never actually touch y equals 0, as we just saw. So what's the solution? The solution here is to define a window here, or a range, by which if a number lies within this range, then I claim that it's essentially 0. So in this case, the way I drew it made it look like there were multiple numbers. But what you could do is make the range real tight to where I don't catch more than one number. So let's see that in action. And then we'll see we're actually able to find the roots. So to do this, I'm going to need the math library. And so we'll define some tolerance. Right? So it's right there. And then we say this. If the floating point absolute value number. So in the math library, there's an absolute value function for integers, and then there's one for floating point numbers because they have different input values. This is the one for floating points. I'd want to see if the difference between the number that I produce, y, and the number I'm trying to get, which is 0, so I could just left that part out. If the difference is very small, which is in this case is my tolerance, then I want to print my number. So there's 3 and 8. Because both of these numbers, because my tolerance here is about at this level. So in that number of decimal points, it is 0. So these numbers are extraordinarily small. So in normal cases, we would consider that essentially 0. So here's how I found it. But I didn't get there by using equality. I just said if it's really small, do this. Whereas the programmer, I decide this. If I did something else, maybe I'd get different results. Let's find out. I don't actually know. So it still worked because these are still smaller than this. But as the programmer, I choose. So there would be cases where this wouldn't be very good, 0.1. So maybe I do what I had before. There, right there. So anyway, that's some things to think about when programming using floating point numbers. You can't represent absolutely any decimal value. There are holes, even though we have a large range of values we can represent, but there are holes in that range. And overall, my discussion here has been simplified. So if I think there's some interest, I may do a separate video discussing the IEEE 754 standard to some degree.